Welcome viewers to the second session of Module 8, that is Design of Spring of course Machine Design. In this we will be discussing number of turns, free length, buckling load, spring surge and spring manufacturing in brief. So what we have discussed till in our last session, that was session 1, is about these four aspects. First is the stress distribution, that is this first aspect, stress distribution. The second aspect is the design equation. Third aspect was the design stress for plain carbon steel, and fourth was the design stress for alloy steel. So you can pause the video or you can go through this the previous video once again, and then we can proceed further. The other aspect of design of spring is to obtain the number of turns, and when we apply some force F on this spring, it is deflected, and this deflection may be of delta y when we increase this load F by to F1. So in this case we have started load from 0 and now we have reached F. At that particular instance we have taken this as reference, and we have taken one fiber starting from the center of this wire cross section as our reference, and when this load F is increased to F1, this change in the deflection is delta y1, and this delta y1 is the deflection corresponding to delta F1, where delta F1 is nothing but it is F1 minus F, that is the change in the load, and this is the change in the deflection. And if we observe the fiber which was taken as reference, where this fiber will go, whether this fiber will remain here or the fiber will take this position, or this fiber will take this position, or in another sense we can say the fiber may move clockwise, anti-clockwise, or fiber may move clockwise. So let me ask you, in which direction this fiber will move, or it will remain stationary? So your answer should be that this fiber will move in the direction of the twisting moment, and from our first session we found that the direction of twisting moment is like this for this type of load. So it means that fiber will take this position. Now if we further increase the load, and let us assume that the change in the deflection is delta y2, here this delta y2 will be corresponding to this delta f2, and this delta f2 is nothing but f2 minus f. And if we assume that this spring to be linear, it means we assume that the load and deflection curve of this spring will take this type of straight line relationship. The spring may be soft, and the soft spring curve will be like this, and the hard spring curve will be like this. In this case the slope is becoming 0, and in this case slope is becoming 90, and this slope of the spring is represented by the stiffness of the spring. So if we assume, let us say that this is the F initially, and this is the reference y, and here we are moving to F1, and here we move to y1, and this change in the deflection is delta y1, and here this is delta f1. So for linear spring, this delta f1 over delta y1 will be equal to delta f2 over delta y2, because for linear spring k is constant and this is equal to k, that is the spring stiffness. When we this representation shows when we apply force here on the spring, some work is to be done. because it is moving through some distance, that is and work done we can get by calculating the area under the curve. If we want that how much is the work done in this up to F1, then this total area is to be obtained. If we want how much work is to be done from when we start from at F and reaches to F1, then this area is to be considered as work done. And for this work done, the energy is stored as strain energy of the spring wire. And what is the strain energy of the spring wire? That is given by, we can understand this by if we plot the moment, twisting moment versus theta, that is angle of twist curve. And this curve within elastic limit is also a straight line, that is mt, and theta, that is strain within elastic limit. So it means this is mt and corresponding to this is mt1, and likewise we have this delta theta 1, delta theta 1, and we can find out what is the strain energy. That if we start from 0, then it is half mt into theta, and if we take the corresponding to only change in the load, then it is half delta mt1 into delta theta. So this is how we can find out the strain energy. So work done by the force is equal to the strain energy due to the twisting moment. So we can write this as half half delta F into delta Y is equal to half delta MT into delta theta 1, or we can call it as delta MT1. Here we can call it as delta F1. Half and half will cancel out. We can replace this theta, delta theta, using our torsion equation that gives us mt by j is equal to g theta by L. Why we are replacing this? Because we want some measurable parameter only, but theta is not directly can be measured. So we want to eliminate this theta, and we want to have all such parameters which are easy to calculate. So L also we can change the L, where L is the length of the spring. This is pi d into number of turn I, and this J is the polar moment of inertia. We know that it is pi by 32 d raised to power 4 for this. So if we substitute everything together, we get value of delta y, that is equal to 8 delta f c cube I divided by g d, and where c we know that is spring index given by d by d, and this we assume depending on what is the space availability for the spring. So from here we can also find out the relation of spring stiffness, that is delta f by delta k. So if I take this y here and take everything in this numerator and this in denominator, we get k is equal to g into d divided by 8 c cube I. And from here we can also find out the number of turn, that is the active number of turn. It is given by I is equal to delta y g d divided by 8 delta f c cube. So this is active number of turn. So active number of turn means which takes part in the deflection process. So now let us see how the total number of turns are obtained. So for that we have four different types of AND, that is plain AND. First it is plain and grounded, this is square and this is square and grounded. So plain AND, when we cut spring from our machine, it is the plain AND. The point of contact is point here and point here to the contacting surfaces unless until they are deflected, and every coil takes part in the deflection. So that is why the total number of turn is equal to active number of turn that we get from the expression that we have derived in the last slide. And here if we grind this, then it is plain and grounded this and in this case the area of contact is surface. So we have surface area contact, but not not the complete circle of the surface. So in some of the text we can add half turn to get total number of turn, but it may be the equal to active number of turn, but it is better to add half here. In case of the squared AND, what we do, we bend this AND to make it the plane of this last coil and perpendicular to the axis of this coil, so it is square AND. And in that case the the contact area is line. It means we have this type of contact, that is line making a circle or arc making a circle. And in this case we assume that it is not every coil is not taking part in the deflection, because it is already attached or touching the ground, and here we have this complete surface in contact with the supporting surface. So again here also we take total number of turn is equal to I plus 2, because here also we get the two surfaces are not taking part in the contact in the deflection process. Then free length is equal to is given by the solid length, y initial, y working and clash allowance. Solid length is the length when we compress this spring to touch a successive coil. Y initial is the initial load when we apply initial load on the spring, because every spring and mechanical system is to be subjected to some amount of minimum load, and what is the deflection at that load is the initial deflection. Y working is once we have given initial load, and then the load may increase, whether it is a clutch type of problem or it is a safety valve type of application. So in everywhere we need some working deflection in the spring. So that depends on how much deflection we want during the working of the spring. If we do not have clash allowance, in that case when maximum load is applied, the coil of the spring will be in contact with each other. So we do not want that the coil of the spring is in contact with each other, and that is why some clash allowance is provided. Means we do not want clash of these that will increase wear and tear, and the noisy operation will also be there. So this is how we can find out the free length, and solid length is given by this. Further, when we have spring, because spring is generally a long member, it may be supported well, but it may not be supported. One end may be fixed, another one end may be pinned, another end may be freeze, as we have the different end conditions in column. So it may buckle. Just to estimate whether this will buckle or not, we introduce one factor. It is the ratio of LF and capital D. So if M is less than equal to 3, we call that the spring will work fine. The buckling possibility is less, and when M is greater than 3, the spring may buckle. But in some of the cases it is not possible to change any of these parameters due to the design constraint, and M is much greater than 3, then we have to suggest as a designer that this spring should be guided. We should provide guide in the spring so that the spring does not leave its place. Secondly, we can also calculate the crippling load, that is the buckling load or the critical load. It is given by K times KL into LF, where K is the stiffness of the spring, KL is buckling factor. It is taken from this graph where KL is the buckling factor. Depending on what is the value of LF over capital D, we get KL from this. For example, if we have M is equal to 3 for this, this curve is for hinge end, and this curve is for built-in end. Built-in end means it is fixed at both the ends. So in this, for hinge case, we have the value of KL as 4, and for built-in end we have a value as approximately 0.68, which is just less than 0.7 if we see this curve. So this is how we can find out the free length and design for avoiding buckling. If it is not possible, then we should suggest that it should be guided. Spring surge is another important aspect in in springs, because when we apply sudden load or impact load or dynamic load, in that case the compressive wave is generated, and that compressive wave moves from top end to the bottom end. If we have this spring and we apply sudden load F here, or we have the dynamic load, in that case the compressive wave that will propagate from this to this and then reflected back to this, and this phenomena of moving the compressive wave back and forth is known as spring surge. If the frequency of applied load and the natural frequency of the spring is very close to each other, then the resonance takes place and spring fails. Most of the failure in wall spring is because of this resonance problem. So the equation of compressive wave that is developed here can be written like this: del u square. This is equal to m over KL square del 2u by del t, where this is the uh, deflection of any point on the spring. Y is the direction that we are considering this as y. M is the mass of spring, K is the stiffness, L is the length, and T is the time. The solution of this equation for one end at one end supported and another end free is this, that the natural frequency is given by, it is 1 by 2m. If both end fixed, then this is given by 1 by 4 k by m, and m we can find out it is area into area, that is volume area into length into density. Area is nothing but it is pi by 4 d square, length is pi d into I, and density is density. We can substitute these to get value of m, and finally we should have this natural frequency of the spring. It should be very high, 10 to 15 times higher than the frequency of this load. Let us summarize this. In case of spring surge and resonance, spring vibrate violently both laterally and longitudinally when loaded dynamically close to its natural frequency. And to avoid this, we can have spring damper, spring with higher natural frequency, variable pitch near the end, means we can have this pitch here, and then this pitch here, and then this pitch here. So if we have pitch is the distance between two consecutive coils. This is one of the method to avoid spring surge. So this is helical spring manufacturing, a simple machine that we see here. The wire is fed through these rollers, which one push the wire and also straighten the wire if there is any bend in that. Then we have these plungers, one, two, this is punch, and first this comes as wire reaches here, this comes and give the direction of the spring here, and once the direction is there, then this is adjusted so that a particular diameter, coil diameter is done, make, and when it again comes here, then this plunger is lifted and it adjusts the pitch. So this adjusts pitch, this is the direction, and this is the coil diameter. And once we get desired length, this is drop down, this and this punch, this is basically punch which cut this spring up to the desired length. So thank you very much for being with me throughout this lecture, and please subscribe, like and share, and please comment if you have any problem or you need that some other type of lecture is to be planned first of your choice. It may be some even design problem, or it may be some component, or it may be some topic. You can just basically give me in comment, so I will be preparing those lectures.